Welcome back to General Chemistry on Catalyst University. My name is Kevin Tokoph. Please make sure to like this video and subscribe to my channel for future videos and notifications. In this video, we're going to do a second example practice problem with heat capacity. Again, it's still going to utilize this formula Q equals smΔT or Q SMAT. But in this case, we're not going to be solving for Q. That was the easy case we did in the previous video. Here, what we're actually going to have is an unknown temperature, either T2 or T1. So let's read the problem that we're going to be doing. All right, so I've got 20 kilojoules of thermal energy, so that's my heat, was transferred to 100 grams of water initially at 10 degrees Celsius. Calculate the final temperature of the water after heating. All right, so we know we're going to have to calculate the final temperature T2. So let's figure out what we know in this problem. All right, we know the specific heat of water. That we covered in the previous video. That's a constant you either have to memorize, be given directly, or if it's homework or something, you can look it up either online or in a book. That specific heat of water is 4.186 joules per gram per Kelvin, or 4.186 joules per gram per degree Celsius. Now again, this is a type of problem in thermochemistry or thermodynamics where we do not have to convert to Kelvin. Leaving these temperatures as degrees Celsius is perfectly acceptable because we're not dealing with an absolute temperature, we're dealing with a change. When we deal with a change, it's okay to leave it as Celsius, or degrees Celsius. So I'm going to keep this second form of the constant S, our heat capacity. We know our heat is 20 kilojoules, so Q is 20 kilojoules. Now, because my specific heat is in terms of joule units, I'd like to convert my heat to joules as well. So to convert 20 kilojoules into regular joules, I have to take this number 20 and multiply by 1,000. Okay? So when I'm going from kilojoules to joules, always multiply by 1,000. So 20 times 1,000 is 20,000 joules. My mass is 100 grams, and my initial temperature T1 is 10 degrees Celsius. So I need to calculate T2. This type of problem where especially you're solving for one of the temperatures is going to require some algebraic manipulation. So we're going to use this second form of the Q SMAT equation, Q equals SM times in parentheses T2 minus T1. Be very careful that you leave these parentheses here. If you lose one of these parentheses, it can be very easy to make an algebra mistake. All right, let's start by plugging in some things that we know. Our heat, Q, is 20,000 joules, equals S, our specific heat of water, 4.186 joules per gram per degree Celsius. Our mass of water is 100 grams. Now, again, parentheses, make sure you leave those. T2 we don't know, minus 10 degrees Celsius, which is our temperature 1 or initial temperature. All right, now, what I'm trying to do ultimately is solve for T2, okay? T2 is part of this term right here, so I need to get rid of everything else on the right side. So what I'm going to do is I'm going to divide both sides by the S and by the M. Okay, so here I've done that here. I'm going to divide both sides by 4.186 joules per gram per degree Celsius and by 100 grams. So I've done that over here on the right side. I also have to do it to the left side. That's just rules of algebra, right? And notice they cancel here on the right side, and so all that's left on the right side is T2 minus 10 degrees Celsius. Meanwhile, over here on the left side, I've got 20,000 joules divided by 4.186 joules per gram per degree Celsius divided by 100 grams. Now, I can now directly deal with T2. I can actually add 10 degrees Celsius to both sides. So let me add 10 degrees Celsius to both sides. If I do that over here, it cancels it from the right side, and then it moves it over here to the left, okay, plus 10 degrees Celsius. So my final temperature, T2, is going to be 10 degrees Celsius plus this entire quantity, 20,000 joules, divided by 4.186 joules per gram per degree Celsius, divided by 100 grams. When you do this in a calculator, and this is because it's easy for people in general chemistry to make mistakes like this, I would always multiply out the large quantity first. Don't enter the 10 into your calculator first. That makes it, even for an experienced person, much more likely to make a mistake typing something in. Calculate this thing first. Okay, so what I would do in my calculator is type in 20,000 divided by 4.186 divided by 100. Enter, or return, whatever. get a number, and it turns out that number would actually be 47.8, and then add 10 degrees Celsius, and you've got 57.8 degrees Celsius. And that is my final temperature, okay? Now let's actually make sure that makes sense, right? The temperature goes up from 10 degrees Celsius to 57.8 degrees Celsius, right? It goes up. That makes sense because I'm adding thermal energy, right? Because I'm adding heat to my system, which is water, okay? So if you're adding thermal energy to your water, to your system, then that's going to be a positive heat, and then the temperature should increase. If this Q was negative, that would be I'm cooling the water, maybe putting it in the freezer, and this temperature would actually go down, okay? So my answer, at least the number itself, makes sense. And that's pretty much all there is to this heat capacity problem. Again, it's more algebraically taxing than we saw in the previous video on this problem, but you solve it the same way every single time. In the QSMAT problem, you look at all of these, really 5 pieces right here, Q, S, M, and both temperatures. You're going to be given 4 of them. You're not going to know one of them. You solve for the one you don't know. In the first example we did in the previous video, we did not know the heat, so we solved for Q. In this video, we did not know the final temperature T2, so we solved for T2. Okay, that's pretty much all there is to these problems. The one thing you do need to remember, though, is that you do not have to convert these temperatures to Kelvin. Okay, you can leave them as degrees Celsius. That being said, that is only the case when you have change in temperature. Okay, if you just had something that just said T, like you have in the ideal gas equation, which we'll cover much later, you have to convert that to Kelvin because it's not a change. Because this is a change in temperature, it's okay to leave it as degrees Celsius. Okay, if you feel more comfortable just by default always converting to Kelvin, you can do that. You'll still get the right answer. But here, you can just leave it as degrees Celsius. So hopefully I've explained this problem well enough and you get a good understanding of heat capacity problems. Please make sure to like this video and subscribe to my channel for future videos and notifications. Thank you very much.